Hi everyone, and thanks for being here. We're going to be talking about collision avoidance patterns that we've observed in virtual dense crowds. One of the earlier projects that we did was for a building in downtown Ottawa that was going to have a light rail station built underneath it. And this was going to sort of relieve pressure off of a lot of bus lines that were heading downtown. And as you can imagine, being downtown, you're going to expect a lot of foot traffic and a lot of commuter traffic. And so the building in general was spacious enough to handle traffic, but they were worried about a couple of bottlenecks, especially around an elevator corridor, and whether how much the new commuter traffic would affect the tenants of the building and their ability to get to their offices basically on time. And so we did a case study. We used a grid-based method that was great. It was good enough for this, and it gave us quick answers for things like the average wait time at the elevator lobby, or the average density you can expect around rush hour, and so on. And again, for the type of densities that we were dealing with, it was a really good method, really fast. It didn't really need to delve too much into the sort of microscopic details of collision avoidance, and it worked really well. But then we came across this question of, what about this? Right? How could we simulate this? And this is not an airport, by the way. This is just a train station on Chinese New Year's. And so the existing methods struggle with two issues about this. First, the fact that the density changes when you're getting towards a point of interest or a congestion. And this is true for both moving crowds and static crowds. And the second thing is that people actually start behaving more like a fluid at high enough densities, right? But they behave like solid particles in sparse densities. So you need a method that can seamlessly switch between the two, depending on the density, depending on the context. And so we created the centroidal particle dynamics method, CPD, which models the personal space as a compressible area, not a one-dimensional distance, but a fully compressible area. And it's completely agent-based, so we're able to reproduce a lot of the behavior, the correct behavior, as emergent phenomenon, basically. And so we took data from existing experiments to extract some metrics out of it, and fed that into our model. We created these virtual personal spaces, and we wanted to see if we could reproduce some key behaviors just completely in an emergent way, completely organically from the local rules, and we were quite successful with that, especially for dense crowds. And we published this last year, and we gave a GPU-based description of the method and how it works. And we ended on a note of saying, look, this would be interesting to use for contingency planning. And one of the important things to do before we can use it for safety critical applications is to validate the method to the point where you can safely say, okay, this really represents reality. And so the paper that we have today is sort of two steps in that direction of improving validation of this method and improving the trust in this method. So we're doing two things. The first thing is we're explaining the underlying model a bit better without sort of mentioning the GPU explicitly. We're decoupling the GPU from it and giving you sort of a more raw representation of what the method is like, and discussing how the personal space map is built, and the forces and the positional advection equations are without bringing in the implementation details. And so this opens the door for maybe implementing this in a more formal model, and sort of integrating it with existing frameworks. So we'll see where that takes. But you can find all the details in the paper, as much as we can cram into a short conference paper, but certainly a step in towards a better validation of the method. Now, the second thing is basically observing the behavior of these virtual crowds and seeing if they match reality or not. Right? So we did more of that this year. And so the first phenomenon is bidirectional flow, right? And this is basically where you have two opposing flows, and there's this lanes. There are these lanes that form organically without any organization, and the lanes are sort of like sneaking through the flow. There's a lot of merging and branching, and it looks a little bit random, a little bit organic, and it's a hard effect to reproduce. And this is not just limited to narrow corridors. This could also apply to a situation with really wide corridors, or at festivals or big fairs and so on. And so this is CPD, running bidirectional flow, and you can see that we're able to reproduce those sneaking patterns quite convincingly. This is completely emergent, and we were happy with this, and we published this last year, and it was pretty great. And like we said, this existing methods in state of the art sort of struggle with this because they don't have a 2D area that's compressible. They get to a point where people behave like pebbles, basically, or stones. They can't really go through each other. It fails. At high enough densities, this fails. Whereas ours worked well. This continues to be true this year as well. So there's stuff from SIGGRAPH where they also struggle to get that natural sort of bidirectional flow, lane formation happening. Now, in order to take that step further and see if our method is correct, we traced out the paths. So if you imagine, like, throughout the lifetime of every entity, there's just traces out the path that it's walking through, and you can very clearly see the interlocking sort of lanes that are appearing. Now, what's really cool about this is that you can then compare it to the real traces of real motion. So that's what we did. On the left hand side is a trace of the actual motion from that video, and on the right hand side is the trace from pedestrians, our virtual pedestrians, in a much wider corridor. And you can see that, like, in a relatively similar sized width, we're getting very similar patterns to reality, which is not bad. And what's really encouraging is that we're able to sort of extrapolate this to a much wider corridor, which is harder to find real data for and to compare. So this is a good sign. Another thing we were looking into is whether we can reproduce the change in density. In uniform flow, we've tested this out in sort of like marathon-like scenarios where there's this acceleration wave that moves backwards, and we're able to reproduce that convincingly because everyone tries to maintain their personal space while trying to compete with each other. And we were happy to see that we're also able to do that for bidirectional flow, which has a different sort of set of characteristics for the density. It starts out fairly even, and then it gets really dense in the middle of in like the most congested areas of the bidirectional flow. And by the time sort of the flow ends, and everyone immediately starts fanning out and regaining a lot more of their personal space than earlier, and we can see that happening also in the virtual crowds. So we're happy about being able to reproduce that completely, again, organically, without any sort of global switches or anything like that. Well, we started looking into specializing subsets of the crowd. So, for instance, here's a couple of friends, let's say, that are trying to meet each other, and they're walking across a bidirectional flow. And you can see them struggling a little bit because they're not going along with the flow. But still, realistically, they're getting through until they meet each other. So we're doing tests like this to see, if does it make sense to, like, what would be a nice placement and arrangement of, let's say, a stalls in a fair or a festival or a carnival around a highly trafficked path, right? So maybe it's a good idea to put two things that are very popular, to put them right next to each other so that people don't have to cross bidirectional flow too much. Another one is looking into people that are traveling as a tiny flock, a tiny group. Again, here they also struggle to sort of go across, but they all would also try to stay together as close as possible to each other. So if one of them lags behind, the others will sort of wait for them. And we see here that they were sort of like pushed away by the rest of the crowd, but which makes sense when you're trying to go literally against where everyone else is going. And what you're seeing here is their force vectors of like cohesion and where their target needs to be, and I think one more is about to catch up. Yep, and they get to their target. So we can do studies on that for things like families and maybe VIP groups, or even tour groups that are in really high density areas. There's also the cases of intentional congestion, right, where people are just standing around and sort of cause a bottleneck for no reason. And we're doing studies on this to see, first if we can reproduce what happens in reality, but also we're noticing things like, it doesn't take a lot of people to cause a congestion. On the right here, there's a few people that are standing still, and you can see it doesn't take long for them to start causing everyone else to file into a single line, basically reduce the flow to be a single line. So okay, you expect that in a narrow corridor, but what about a really, really wide corridor? Is it okay for a bunch of people to stand in the middle and not really move? Well, on the left-hand side there, it's a full bidirectional flow. What happened on the right is kind of interesting. So you expect a congestion to happen around the area of people that are the area that people are blocking, but what was really interesting here is that congestion actually started forming around other pockets nearby, and basically it was going across the width of the corridor. And when we saw this, we were like, that actually makes sense, right? If there's an accident on the road, it doesn't just block the lane that it's in, it slows down all the lanes across the road, because now a lot more cars have to share lesser lanes, right? So that was an interesting phenomenon to see, like, virtually, just completely emergently happen. Right? Now we're also able to tell our crowds to be a bit more aggressive or less aggressive, based on whether they respect the personal space of other people versus their own target vector or where they need to go. So we can do experiments about this, of like highly competitive artificial scenarios where people are congesting over an area, but it's sort of testing the limits of how people behave. But what's interesting is the one on the right here, where we can use obstacles to guide the flow passively in a better way, right? So if you're designing let's say a mall area, this could be a bench or a fountain in the middle of a critically busy area. Could this obstacle passively help the flow in a certain way? Perhaps. And so you can start running an optimizer on this and try out different shapes of obstacles and see if they can help improve the flow of traffic, right? See if you can reduce the peak density experience, the time to arrival, and all kinds of metrics that are relevant to you as a designer of that space. Now very quickly, we're going to conclude by mentioning some of the limitations and opportunities. So we talked about how data validation is basically about finding statistical similarities. We're not entirely there yet. There's more work to be done. But an interesting note is, could machine learning feed back data into the model? Because it has a full 2D area to work with, so could AI tell us like a nice weight map to apply on that 2D area to reproduce realistic results? And there's a bunch of other additions, like having better visualization and improving the scalability of the algorithm. Could we simulate an entire city block with it one day? We're hoping so. Thank you very much.